full time, like working out. Yeah, the full time is like working out.
So for example, I was going into a building, and there's a stream of people going in. I don't see class. There are two doors, only using one. Someone's standing in front of that other door waiting for the wall. And then they just sneak in between all of us. Like, I think it makes me more angry than anything
Yeah.
like on a day-to-day basis.
I was kind
No, I'm just saying, like, on a day-to-day, when I get to this point,
I was just like,
I'm just really
how
I already the other girl
actually
and no one knows email just because they used to be the square account. So we can't get it as a square account because it's stupid. Right? So I make an email with EE5393 and right? Oh my God, there was one associated with EE and then you and I was using the password. And I was like, yeah, because I made that account. Like, well, they should be linked in. Like, the money should be available. No, it should not be. They are not. You know
So they were using you use your signature as people, right?
they made the computer last year, basically, two of them. And they each say that they've had it. And they say they made it with this web email. I go in there and I'm like, forgot my password. There's no accounts with secret email.
no.
There's no.
But that one I didn't have.
Needed a square. Yeah. Logically, with the okay, I get it. And I just tested the EE numbers. It seems like there's an account. I was like, yeah, idiot. And then she was like, oh, so the money must have transferred into that. No, not at all. They were so.
I was actually gonna do it because I didn't
So you have a lot of stuff in your backpack. And they each have like they have varying things about what's I just what is the most valuable configuration?
This book is
I mean, it's not that big of a deal. I mean, like, just write a function that.
So how is Robert's dad?
There's a connection to like somehow like taking average that. Doing like some of that. It's gonna be make
Yeah, I know she wants to do forensics. She wants to do
Because then it's like you square it, instead of probability, then it's connected directly to two. And so you have first square root and then plus the square root plus
yeah. Good.
and then it's
You're good.
Okay, let me talk a little bit about the homework. I'll open it up first if there are any specific questions on it for those of you who had a chance to look at it. If not, I'd definitely like to clarify a couple of things for the fourth problem. But first, any questions or concerns in general? Yes?
On problem 4, you could scroll down.
Yeah.
It reads, for part B, it reads, there are any mobile users who get random location for R probability. Is that R unique for every user, or is it or every user at the same R?
That R is the same for every R. So, yes. So the question was basically, to simplify it, what do I mean by question B? And that's exactly what I wanted to talk about. So let me just make it quite clear. First, clear what the setup is, but then it is vague the way I stated it. I simply ask you, what is the threshold for percolation for N, R, and Q? Let me explain it first, but then let me state that if anyone can come up with a formula for percolation as a function of N, R, and Q, I'll be impressed. But instead, the expectation is that you can simply choose specific values of N and R and then vary Q and say what happens as a function of Q. But first, let me explain. So the setup here is for you to consider percolation. Percolation is a topic that I went over in class without any mathematical rigor whatsoever. And in fact, I regret that because I spent a lot of time talking about it. I simply stated that percolation happens without speaking at all as to why percolation happens. Percolation is the phenomenon that if you characterize global connectivity as a function of local connectivity, so whether things are connected globally, according to some measure, as a function of whether they're connected locally, then if you have at least a two-dimensional topology, so if you're working in 2 dimensions, on a line it doesn't work. But if you're working in at least 2 dimensions, and you plot what is the probability that two things are connected to each other locally, or if that's what you vary, and you plot what is the probability of things being connected globally, you get a sharp nonlinearity. So you get a sharp So this is probability of local connection, and this is probability of global connection, where this is 0, this is 1. And this is the percolation threshold. So imagine you've got points. And P local, let's call that P, and let's call let's call that X. Let's call P global Y. Probability of X is whether this guy is connected locally to any of his neighbors. So let's say each edge here is an edge with probability P, with probability X, and it's no edge with probability 1 minus X. then what is the probability that everybody's connected? Or if I pick two randomly spaced points far apart, what is the probability they're connected? That's the probability y. Obviously, with x is 0, if nobody's connected to his neighbors, then nobody's connected globally. But as I increase x, initially, pretty much no one's connected to their neighbors, and then suddenly, bam, everybody's connected. So that's percolation. That's how I described it. But what I didn't describe at all is why this happens. I'm not sure that I really can. It's the mathematics dictates it. But does anybody have any intuition here? Yeah.
Well, the mathematical induction works for this problem. Because first you can consider just two elements in this system, and the probability of the local should be the same as the probability of the global, right? And then you consider the two groups of them. And you suppose every group are connected globally. Well, this works.
Sort of. To me, that doesn't immediately give me the intuition. I can't really speak much more about this. It's not, mathematics aren't part of this course. But just to comment that when you consider nonlinear devices in electronics, this is the same phenomenon that you see if you have a diode, for instance, or if you have a transistor. It's a nonlinear device in the sense that for a transistor, as you vary the voltage at the base, you get no current from collector to emitter, no current, no current, no current, and then sudden, bam, current. So you get this nonlinear type of response. And what's happening is essentially at a physical level, again, this is outside my area of expertise, but if you think of how transistors are made with silicon that's doped, you have the same kind of phenomenon. You have electrons that can move locally, initially with very low probability when the voltage is low, and then slightly higher probability they can move locally, and then suddenly, bam, they can move much more globally. So it's the same phenomenon. When this nonlinearity that we exploit in conventional electronics stems just from the phenomenon of percolation. So really, I would argue, it's truly a fundamental concept in physics and engineering. And perhaps should be much more widely emphasized early on in a discussion of what is electronics and so forth. But anyways, I introduced this concept because it was one for which I'd done research on with respect to defective switches in a grid. It was a nice application. But for the homework, what I'd like you to do is play around with the phenomenon. And for this, I stated at the outset of the course that programming is not required, and I'd like to stick with that. But of course, for this particular problem, attempting to solve it on paper will be challenging. Because on paper, I guess you can plot some values, you can play around with it. You might not get it very far. But that said, if anybody wants to attempt this without writing any computer code, without doing any kind of simulation, then please state this in your response. State at the outset, I'm solving this by hand. And then it'll be evaluated differently. It'll be evaluated in the sense that calculations, and you'll have to provide a sequence of calculations that you think illustrates percolation happening. So you can try plotting different values, but then you should try plotting some values as a function of a variable that changes. So you should try to do something with math, a little bit of calculus, a little bit of symbolic math. I understand that your answer then won't be as rigorous as somebody who wrote some code to do it, but I'll accept it. Just state it at the outset. Okay, but let me explain what I'm looking for problem B here. Problem A was just what I described exactly here. A graph with n vertices and being connected to a neighbor with probability p. But the next one is the cell tower model of percolation. So what do I mean? At the center, we have the cell tower. And I state that the tower, then there's a radius r, big R. So this is R. And within this radius R, I've got n users, and they're randomly distributed. So n of these guys. And then each of the n users has, for his or her cell phone, has a certain power. Cell phones have a certain amount of power, meaning that their antenna can only broadcast a certain distance. So they each have a radius q. So this is a user again. This is a radius q for a given user in which the power of his or her cell phone allows transmission and communication. And the question is, so if we have a whole bunch of these guys that are q, what is the probability that every user, all n users, can talk to the tower? Of course, the model here is that communication can go hop by hop. Think of a frog on a lily pad. And that's actually, so I don't think a lily pad out here can support a frog. So I think the frogs jumping on lily pads, that's something I've never seen. Like, frog is a big creature, a lily pad's pretty flimsy. Anyways, so a frog jumping on lily pads, if the frog can jump across lily pads and make it all the way to the tower, then that user is connected to the tower. So what am I looking for? Well, it would be great if somebody could figure out how this works for a whole range of different values of n, r, and q, or perhaps a whole range of values of n and r, and then explains what happens for q, where I guess q can range from 0 to r. So if the radius is 0, obviously nobody's connected for q. If the radius of q is equal to the radius of r, then obviously everybody's connected. So q is the knob that you turn. You turn the knob from q from 0 to r. And as a function of that, is everybody connected or not? But what I'm asking for here is the probability, because this only works in a probabilistic sense. So what do I mean by that? Any ideas? Alex. So how is the probability of everybody being connected different from the question, is everybody connected?
Is that the difference between the two probabilities you've shown on the graph?
Yeah, what I'm going for here is that if you're doing this as a simulation, so if you're setting up computer code that will simulate this, a reasonable thing to do is pick a value of, let's say, r equals 1 kilometer or whatever unit you want, parsecs or whatever unit is. And then you can pick n. N is an interesting parameter to vary, but pick some initial value of n like 100. So a 1 kilometer radius, 100 users. And then for q, so this is q going from 0 to r. Here, what I want is the probability everybody connected, which will be from somewhere from 0 to 1. Now, if you set this up as a simulation, you can set it all up with r equals 1, n equals 100, and then you can vary q from 0 to r. And each time, for a specific value of q, you can simulate what's going on. The random part is you'll randomly have to place the n users on the disk. So that's the randomness. So you'll have to use a random function in your code to randomly place the n users. Then you can ask, for that particular, so let's say you're at a value of r equals 250 meters right here. You can ask, is everybody connected to cell phone tower? It's either a yes or a no. So that's one answer. Now, if you do this simulation 100 times, for this specific value of q, 250 meters, sometimes you'll get yes, sometimes you'll get no. That will be an estimate of what the probability is, and that's what you should plot. So here, if, let's say, 0.4 of the time, so 40% of the time, you had everybody connected to the cell phone tower here, this would be the point that you'd plot. And I want you to plot that. And what I'm hoping you'll get is you'll get something like this, which illustrates percolation. And then the answer that I want is, what is this distance here for which percolation happens? And so for your homework, feel free to use r equals 1, n equals 100, and vary q. But it would be nice if you could also vary n. So then this would be a whole sequence of graphs, or it would be maybe a two-dimensional graph. That would be really nice. So three-dimensional graph. So in the third dimension, you could plot the number of users n to show a curve. Or even nicer would be, I don't know how to do it, but if any of you can come up with, if not a formula for when percolation happens, an attempt at a formula describing the function. Yes?
So the radius have to be within that radius r?
Pardon me?
That's given, right?
The radius r? Yeah.
Everyone has to be within that radius r.
Oh, yes, that's a good question. So can people be outside of r here?
Yeah, and then could still be connected
If their edges touch? But no, let's put everybody inside of the disk. I don't see any benefit to not. Okay, yes, Tor.
So if a single user is not connected, is that just considered a false?
It is.
Okay.
You're a good cell phone company. Unlike the crappy cell phone companies there, you're really concerned about every user. Very consumer-oriented here. No. Yes?
I have a question about part A.
Yeah.
So the edges between the neighbors, are they necessarily bidirectional? Like, is it one connection for each if they have an edge between them?
Yeah, that's a good question. So yes, bidirectional. But because here, yes. So it's not as though you'll be connected to your neighbor, but he won't be connected to you. It's always bidirectional. But maybe you're asking something more specific.
No.
No. Okay.
Because in the second one, it's implied that it's bidirectional.
Yeah. Mackenzie?
To connect with the tower, does the person's radius actually have to touch the tower, or does the tower have that radius q as well?
No, it has to touch the tower. That's a good question. There's always these details that I don't think of. Because in a realistic model, the tower would have some broadcast radius, which might be larger. That would be another parameter. But here, let's say that the user's disk just has to overlap the tower. So the tower has zero power, as it were. Okay. Any questions on the other ones? Anything at all? Just number two.
Just when you're on your examples,
Yeah.
how did you determine systematically how to incorporate the inputs with the probability?
Yeah, that's a good question. So I'd say the last one, I've explained it, maybe not so bad, but this is definitely the difficult problem on the homework. So the key, but it sounds like you understand the entire setup, right? Okay. Perhaps to remind ourselves what the setup is here. We've got a circuit, just an ordinary logic circuit. Here the setup is, we're asking, what is the probability of getting the wrong answer? What is the probability of getting the wrong answer as a function of each gate giving the wrong answer? And wrong here is a very clean concept. The right answer is what happens when there are no gate errors. So that's just what the function is. The wrong answer is if we get the opposite. 1 when we're supposed to get a 0, 0 when we're supposed to get a 1. A gate produces either the right answer, which is what it's supposed to produce in terms of 0 or 1. The wrong answer is the complete opposite. So everything is just 1 flipped to 0. And the premise is that for each gate, there's a parameter epsilon, which tells us the probability that that gate fails. So for a given input combination, like if an AND gate receives 2 1s, it's supposed to produce a 1 at the output. It produces that answer 1 with probability 1 minus epsilon. And with probability epsilon, it produces a 0. It produces the opposite. So epsilon, and the epsilon parameter, we could have introduced a separate epsilon parameter for each gate. But let's just have one epsilon parameter. And that epsilon parameter also applies to all input combinations for a gate. So if you think for a given AND gate, for a given AND gate, if we had the 0, 0 combination, we're supposed to get 0. Here we can say that it produces a 1, which is a fault, with probability epsilon. But we could also, for a general model, have a different parameter epsilon for each input combination. So for 0, 1, perhaps the epsilon is now different. And in a realistic circuit, it would be different, because if you think of it, the AND gate, given two 0 inputs, might be less likely to fail than only given a single 0 input in terms of producing the wrong answer. But anyways, one parameter epsilon for all input combinations, the same parameter epsilon for all the gates, but the probability of failure of the gates is, of course, independent. So the one gate failing is independent of the others. Okay, I think everybody's on board there. But the question is, how do you go about computing the overall failure probability of the circuit? The reason why I gave you this problem is that for such a simple circuit, circuit B has 3 gates. This is a pretty scary looking formula. It just illustrates the mathematical richness, I guess, of these types of computations. But to answer Jason's question, how do we go about computing this? So I think the key is because you'll notice the probability of failure here is a function not only of epsilon, which you'd expect, but also the variables a, b, c. So what does it mean? It means here that if c is 0, then the probability is epsilon. If c is 1, then it's epsilon minus 2 epsilon squared minus 3. So we have a Boolean variable, a variable that's either 0 or 1, c, mixed in with a probability calculation, which is not perhaps so common. You expect a formula to either be 0 in terms of zeros and ones or in terms of something like probability. So that's your question, right? Okay. So how to go about doing that? Well, I want you to struggle with this a little bit, but the key is to break it down by truth table, because here, if you break it down by truth table, here you're examining all possible input combinations, and for each input combination, you can go and you can decide if a gate fails, whether that gives you the wrong answer. So you can get the probability of failure for the circuit in this form. I think that's straightforward. But then the question is, how do you go back from that to a formula that contains A, B, C's? Well, what you can do is, obviously, we're assuming that each row of the truth table is an independent event. So you can compute the overall probability of failure as the sum of the probabilities of failures of the individual rows. And then for each row, you can describe, in terms of Boolean variables, what is the function of getting that row. So I'm not stating this probably, because it's not the sum of the probabilities. Okay, let's put it this way. So for this hypothetical circuit, if you were to write out what is the probability of the failure? Well, the first row of the truth table is when A, B, and C are all 0. And so if you write down A naught, B naught, C naught, this is going to be in a probability calculation, but I'm going to put 0 and 1 variables in with it. So here, this is now going to be a term in a summation that will only be 1 if A is 0, B is 0, and C is 0. And here now, I can put a value. And that value will include an epsilon. Then the next term will be something like A naught, B naught, C, which is now A being 0, B being 0, C being 1 times something. And the probability calculation makes sense because this way I'll have 8 terms, and each term, for any given row of the truth table, only one of these terms will be 1. So I'm picking out the correct case in the probability calculation. And then I'll accept an answer that's just written out like this. You don't have to simplify it the way that I do. But you could simplify it by, once you have a formula in terms of Boolean variables, using logic simplification techniques to combine the variables. Does that make sense? Think about it a bit, and then let me know if you're still struggling with that. Or if anyone else has questions or comments on this. Yes, Rowan.
So I guess if you have like 8 independent events,
yeah.
Why couldn't you just multiply each of the probabilities by 1/8 and then add them to get like a total probability of the series?
Yeah, let me think. You can. trying to think about this. I'm not doing so well in real time. Because here I'm not talking about, I don't know if we're implicitly assuming that each row of the truth table is equally likely. I think we are, but I don't think we even have to assume that. Yeah, John?
Doesn't it deal with one gate, two gates could fail, but you still get the right answer?
Yeah.
So that's why you can't do that probabilistic method of just saying if a gate fails, what are the chances?
Oh, sure.
You could end up with the right answer after failing multiple times.
Yeah, absolutely. So the problem is trying to illustrate that in circuit A versus circuit B and this table, these two circuits compute the same function. But what it's attempting to illustrate is that the probability of failure is different among the two. So it obviously, as John is saying, the point is that sometimes a gate can fail, but you still get the right answer. And that happens with logic because zeros and ones, you can have a gate produce the wrong answer, but still the right value of zeros and ones pops out. But what I'm puzzled about as I'm trying to think about this is when we do the probability calculation, how do we deal with rows of the truth table? And that's, I guess, exactly Jason's question.
The formulas kind of look like they had A, B, and C fixed.
They had A, B, and C fixed.
If you input this A, this B, and this C, then what's the probability?
Yeah. So that's what I want the formula to give. But how do you arrive at that by going row by row in the truth table? And that's exactly the question. And the question is, can you just, as Rowan suggested, view the probability of each row being 1/8? So, what is the probability that you get a given input combination? It's 1/8. And I don't think you have to assume that. Let me think about it. I'll get back to you guys. Yes?
So that question said that for each input assignment?
Yeah.
So could we just give the table and that's it?
You could, the way I phrased it. So the way I phrased it, you don't have to package it into a nice formula, but it would be nice if you could package it into a nice formula. But you guys, I always tell this to the undergrads, you guys are by nature, and you should be little lawyers. And I say this with a lot of contempt. But meaning that on an exam or for a homework assignment, you can be very literal in the way that you answer the question. If the question asks for something, even though you're thinking, well, the professor probably wants something more detailed, you can just give what it answers, and then you can really defend that you provided what it is. So if I say for each input combination, then this suggests that you can specify it independently. Okay. Are there any further questions or comments or concerns? By the way, in dealings that I had, were pretty complicated. This was my family. My mother's side is from Europe, and there's some property that we own there, so I had to deal with international tax laws and so forth, and dealing with lawyers. I had a certain experience, and it was both positive and negative. But here's what I've concluded is the ideal mental predisposition to be an effective lawyer. Obviously, you have to be smooth-talking and charismatic. So you have to be eloquent, smooth-talking. That's how you convince people of things. But here's what makes you an ideal lawyer. You talk smoothly, eloquently, you convince people, and when you're speaking, you speak very logically at first. So you make an argument that just seems very convincing. It's point A followed by point B. This is why point C should be true. Everything is going fine. And then all of a sudden, bam, you say something that's completely illogical, that makes no sense, doesn't follow from anything else, and then you keep going, proceeding logically. It's kind of like a complete little mental spasm that you have. And this was what makes an effective lawyer. It's a lawyer who can argue something effectively. And it's infuriating to talk to somebody like that, because you think you're talking to somebody who you can reason with, and then suddenly, no, that doesn't make sense. And they just continue with their little charismatic, eloquent way. And this lawyer, he could switch between two points of view. One point of view, which is that when trying to interpret laws that are ambiguous, you should go by the underlying principle. If the wording is ambiguous, you should go by the underlying principle. So that's the argument he could follow. But then 2 minutes later, for some different aspect, he could be arguing something that's completely illogical, but he could be saying, no, that's literally what the law says, even though the law, if he was interpreting it. So just switch between literal and principle back and forth whenever it serves you and have little mental spasms. This makes for a good lawyer. As engineers, it's very frustrating to have a conversation with someone like that. Okay. So here's where we were last time. Just a little bit more on how we can simulate a set of chemical reactions, and because I don't want to spend too much time on this, just a little bit on the algorithmic aspect of it. The algorithmic aspect is if you guys had to sit down and write code that went through a simulation of the stochastic chemical kinetics, the probabilistic simulation of what's going on, how would you do it? Well, we've been through the example where you start with a given set of quantities for your molecular types. You compute the probabilities of each reaction happening. Then you proceed according to what's on this slide. So in software, you generate a random number. You generate the random number between 0 and 1. And then the number that you've generated, you can view it as a dart that you're throwing that's landing somewhere on this one-dimensional dartboard randomly. So you throw the dart, and wherever it lands, then that dictates which event you choose. And so your events, R1, R2, R3, R4, you've computed what the probabilities are. You lay those out on your one-dimensional dartboard such that... I thought I had an illustration of what was going on. I sort of do. So if R1 is going to be the probability of 1/8, R2 is 1/16, R3 is 1/8, and R4 is 3/4. You lay them out this way. And it doesn't matter which way you lay them out, which way you interleave them. You can just lay out your values. But the process of choosing which reaction happens is random, but it's random according to the probabilities. And this is how you achieve it. So then in your simulation, this is what you do. You compute probabilities over and over again. You generate random numbers. Based upon the random numbers, you make a choice. You update the quantities, and you do the process again. So what would you guess, if you have to write the code, is the most time-consuming part of this? So Alex, either Alex, you're in a line, both of you. How about Rhea or Alex? Well, if you wrote the code and you ran the code, what do you think would take the most time?
Choosing the random number or calculating the outcome of that random number?
Yeah, I guess so, yeah.
I would say choosing the outcome of that random number.
Mm-hmm. So what do you have to do for choosing the outcome of that random number?
You have to plug that number into a series of equations that solve for wherever your input is.
Mm-hmm. So there's definitely work involved for that. So here, if we were to divide out the steps of what we have to do, the first step is we've got to compute those probabilities. There's work to do that because we have to take the quantities that we have for the different types. In my examples, there's always 3 types, A, B, C, and small quantities. But for the example of the lambda phage virus that I'll show you, there are several hundred types, so several hundred types that have larger quantities. So you have to plug those values in and compute what the probabilities are. It turns out that that's relatively quick in terms of the number of instructions that it takes when your computer executes it. Simply because the probability calculations are very simple. It's just you compute the alpha, which is often just a product, sometimes a product with a quadratic term in it, so a multiplication of product, a few of those, and then a division by all the alphas. But furthermore, if you're clever about how you write the code, it turns out that the probabilities don't change that much. Because, for instance, when one reaction fires, it changes some of the types. It changes some reactants and some products. But if you have hundreds, the reaction may change 2 or 3 out of 100. So most of your alphas, the calculations, your alphas don't change. So you only have to recalculate an alpha when any of the quantities involved in the computation of the alpha change. So it means that for the probabilities, you often don't have to calculate much. So you don't have to do much work at all to compute the probabilities. And then The choice, once you have the random number of which reaction to choose, that's also pretty simple if you lay it out correctly. You've got probabilities, if you have, let's say, 50 reactions, you've got 50 numbers, and based upon the random number which you choose, that's pretty simple. Updating the quantities is also pretty simple because when a given reaction fires, let's say, only 2 or 3 change, you're changing it. It turns out that almost all the work in your code is in generating that random number. So, and this is something, if you're a programmer, and these days programming has gotten so much easier with higher level languages, you just make a function call, you lose track of the fact that that function call, there's software behind it. And generating the random number, the pseudo-random number generator, goes to code that's not terribly complicated. But actually, because most people want very good random numbers, there's a measure of good pseudo-random numbers, it'll execute a pretty complicated function to give you the random number. And so people were really concerned about making the simulation process very efficient here. If they look at it, they say, well, generating the random numbers is taking up all of my supercomputing time. So any ideas or suggestions? What can we do that could make our simulation more efficient? So Jacob, any ideas?
Produce the random numbers in another thread and then just have them available.
Mm-hmm. So just produce them ahead of time, or
like on another core or something.
Yeah, that's true. In this day and age, those kind of techniques are very powerful. In fact, this whole exercise, this is perhaps why I'm not so interested in the simulation part of it. With modern multi-core systems, or even better with GPUs, you can execute things in parallel. This problem, there's a term that's often repeated. This is called embarrassingly easy to parallelize this whole process. So how could you parallelize this whole process? So John?
Similar to what he was saying, you just have something that's constantly generating a queue of random
Yeah,
numbers.
so that's one thing you could do, but you could actually parallelize the whole process. Because your goal here is to generate many trajectories. Many, many trajectories. You start here, that's your initial quantities of... What made people chuckle over there?
I wasn't sure if you were saying paralyze or parallelize.
It's very easy to paralyze the process. I probably misspoke. Parallelize. That's kind of hard to say. So there's this phenomenon called hysteresis in engineering. Have you ever seen this? And if you want to characterize a response that has hysteresis, what do you call it? Do you call it hysteresical or do you call it hysterical? I think you call it hysterical, right? So here, we're not trying to paralyze the whole process. We're trying to parallelize the whole process. So the process here is you start from a given state, and you generate a trajectory the way we've described. And then you've got some stopping criteria. But you've done that once. Because you want an estimate of the overall probability of getting here. What you do is you don't generate just one trajectory, but you generate 100,000 trajectories. So you generate another one, and you generate another one, and you generate another one. And then you collect the statistics, or you estimate the probability by averaging out where you're at, either at the end or at every step. So you do something over and over and over again. You generate the random number to simulate an event. So you use randomness to generate the event, and you use many events to estimate a probability. That's the essence of the simulation. I think it's quite intuitive. But the point is that if you have access to a GPU where you can execute many things in parallel, or a parallel computer, you can launch many independent trajectories at once. And then it's like you can run, if you have 1,000 cores, it's like you can run 1,000 trials at once. Each calculation is simple and independent of each other. So it means that you can greatly expedite the process. But it's obviously not good enough for people over in chemical engineering who, like Yanis, who they really make use of supercomputing time, which is inherently parallel, and they know how to do all of this. And still they're clamoring for faster computers. So maybe there is something to this whole discussion on how to make the process more efficient. But any ideas on, so one idea is randomness, but what can we do that's perhaps even more clever than just pre-generating our random numbers, as it were? Any ideas? Yes, yeah.
Are you asking how to generate such a probability weighted system?
And what I'm going for is that we want to minimize or reduce the number of times that we generate a random number at all. A loop. But there's going to be a loop that's generating our trajectories. But I want some way to not use as many random numbers. Yeah, Mackenzie?
Can you use like one random number or a few random numbers like at the beginning, and then just for each step change how your like probabilities are set up? I guess.
Yeah, that's I think where I'm going. So it's going to be a hybrid between calculating where we're going and then making a random choice and going there. So it's going to be, in essence, a hybrid between doing more calculating and less random stepping. Let me try to illustrate. So this was just illustrating the process. So perhaps did this illustrate this? Just intuitively, imagine that in a given step, the probabilities were laid out like this. A bunch of low probability events, one really high probability event. If we're just using a generic random number generator for a code, it'll generate random numbers with a lot of precision. And in terms of our dartboard, this entire region is a region of the dartboard that's very easy to hit. There's an expression in French, it's like trying to shoot an elephant in a hallway from 3 meters away, meaning you can't miss. So if you throw the dart, it's likely to land in this area. But more importantly, it doesn't really matter if it lands right here or if it lands right here. The outcome's the same. So intuitively, we spent all this time, this computer time, generating a very good random number. This, random, and yet, in terms of where we go, we don't really care about that level of randomness if we're in this region. We do care about it if we're in here. So a dart that's flying in this general direction, we want to keep track of where it lands very precisely. But a dart that's flying in this general direction, just let it fly. So that's where we're going. That's one way to put it. So let me try to explain. So it's an idea which, to be truthful, I never really pursued, called event leaping. So the idea is, suppose that if we arrive at the top, we have 4 reactions with these probabilities, 1/16, 1/8, 1/16. What we can do is, before throwing the dart and choosing which reaction happens, just stop and do a little bit more calculating. So what should we calculate next, Mackenzie? If you had to calculate something, what would you calculate?
I suppose you'd have to notice that there's a big probability in 3 little ones.
Yeah, and once you do that, because there's animation here, what's going to appear next on the screen, if you had to guess? What will I calculate more of before I make a leap? Or which, because we'll call this branches of a tree, it's an upside-down tree, which branch of the tree will we explore further?
Is this in one of the 3 little ones?
It's actually if we're in the big one. Why? Because if we're going to throw the dart and it's heading in the general direction of the big one, then we don't care where it lands. It's going to land there. So why don't we explore that one further? Meaning, what do we do? Well, before making the leap, we can just pretend that we landed here and calculate what would have happened if we landed here and continue the process. So if we land here, I should have illustrated there would be probably, again, 4 branches out. But we can expand the probabilities here without making the leap. So in terms of the simulation, our archer, if that's his word, is that a good metaphor? The guy with the bow and arrow. He's standing at that top target. He hasn't yet decided where he's going to go, but he expands the probabilities this way. Now, when we expand the probabilities this way, it means that, as I described last time, if we create a lattice that's more than one step further, the probabilities become multiplicative along each path. So the probability of going here is 3/4, but then the probability of landing all the way here is 3/4 times whatever this probability is times this probability of going here. So the basic idea is that we can expand the tree in any direction we want to some extent. And a good strategy, it seems to me, is to always expand the tree out wherever there's a high probability until all the remaining leaves have relatively low probability and perhaps relatively equal probabilities. They're all around 1, 2, 3/16. Then you have an evenly laid out dartboard you can throw at. And then the random number that you're generating, you can know ahead of time what relative accuracy it has. You can match the probabilities of the leaves that are in the tree to the accuracy of your dartboard. In other words, keep expanding the tree, keep calculating more probabilities until you've reached the threshold where the probabilities that you've calculated in the remaining leaves roughly match the accuracy of your dart. So then you have this tree. It might be 1, 2, 3 hops, but it might be 10 hops, so it might be a big tree. Then your archer pulls his bow, he throws the dart. So this is a way to match the accuracy of your random number generating, which is the work that you're doing, to the problem at hand, which is where you want to go. And so then, after expanding the tree further, you can make a single leap. So recall that probabilities are multiplicative as you descend. They're additive when they merge. So you have to do that calculation. There is work in doing that. There's definite work in doing that. But as I said before, the work in computing the probabilities, if you write your code properly, is really not that significant. So anyways, once you have the tree set up like this, you can make a leap. Making a leap means that, in essence now, like the idea with cycle leaping, which is jumping out of a cycle, here you've rewired your state space, meaning it's as though instead of the black arrows, you have red arrows that go directly from where you're at to each leaf that you've computed. And then that's your new step. And then you can make a larger leap. So that's a possible idea to expedite the simulation. But those of you who are code-oriented, what are some immediate limitations or drawbacks of this whole approach? So John, if you had to write code, why might you be skeptical about using an idea like this?
The first thing that comes to mind is memory.
Yeah, very good.
But I don't know if that's what you're looking for.
That's exactly what I'm looking for. So speak to us a bit. Why suddenly is memory, the discussion of memory, why is it relevant and why is this a drawback?
Because memory is slow, or can be slow, depending on what type of memory you're accessing.
But what I'm getting at here is that we have to remember a lot more.
Right, and what I'm saying is if you're writing to something that's fairly slow,
Yeah.
that whether it's processing time generating random numbers or writing, if it's still taking the same amount of more time to write to your memory, then you're not gaining anything.
Yeah, absolutely. And so going back to the idea of cycle leaping before, there the burden is even higher. What do we have to remember there that we didn't have to remember with the naive implementation? So we have to remember where we've been. So recall the idea of cycle leaping. This is the idea that we have, we're, let's say, going through a bunch of states like this, and then suddenly, whoops, we come back. So what do we decide to do? Well, instead of going around the cycle, we figure out where the exit points are, and then we try to immediately leap from where we're at to some of the exit points. So that sounds nice and intuitive, but it means that in your code, you now have to keep a history of the states that you visited. Because otherwise, how do you know that you've been there before? You're stepping along, your code is stepping along, doing the calculations. You have to notice, oh, I've been here before, I must be in a cycle. That sounds easy to say, but your code then has to keep a history or a cache of the states that it's visited. That immediately imposes a cost. Why? Because for each new state that you're in, you then have to look to see if you've been there before. You can, of course, do clever things in terms of how you structure that lookup information, but you're definitely remembering stuff. I'd argue that you don't have to preserve a tremendously large history because a tremendously long cycle that you're in is not a cycle that you're likely to go through over and over and over again. The cycles that you go through over and over and over again are probably going to be really small, tight cycles between nearby states. Still, there's still an overhead in remembering where you've been, let's say, for the last 50 steps or the last 100 steps and looking it up. Similarly, with this idea, we have to do some calculating before we make a step. That calculating, I can argue that the calculations are relatively simple, but you still have to set up a data structure. The data structure has to incorporate what are the probabilities in your vicinity, and then you have to make the choice accordingly. So all of this means that your code, not only in terms of the number of steps that you have to write, it's definitely getting more complicated, but then when it executes, what it's doing is more complicated. And if you compare that to the naive implementation, which is just basically do nothing, don't remember anything, you're here, compute probabilities as quickly as you can, sample that random number, and go to your next state as quickly as you can, that's probably going to win out in a lot of situations. So perhaps it's a hard sell for the people who are really pressed for supercomputing time to do it this way. But I still think there's interest in this because at least for small, and I'll show you examples like when we do oscillation in chemical reactions. These are chemical reactions that oscillate repeatedly. They obviously have interesting behavior. And if you simulate them this way, you can see the oscillation. But understanding why the oscillation occurs isn't so obvious. And so you can sit down and just try to be brilliant as you stare at the set of chemical reactions. But I think trying to understand how you calculate probabilities, at least over some region of the space, it can give you insights into why things like oscillation happen. But just a few more words on potentially why the concepts of cycle and event leaping could be effective. Yeah, John.
I just have a question.
Yeah.
Is there anything to be gained if you made a tree like this, and instead of running many computations, you just made one tree, and you have the probabilities of all the bottom leaves getting there, and so now you might not have to calculate all of those paths. I don't know if there's anything to gain.
No, but that's exactly at the heart of it. So for what's surprising, you guys will work on this on the next homework, is that even for a simple set of reactions, even if you take 3 types A, B, C, it's very difficult to compute the complete lattice. Why is it difficult? I don't know. It's a question. Because as you guys will see, I keep saying that. So if we have A, usually the unite markers are nice and crisp. A plus 2B goes to C. B plus 3C goes to 2A. And A plus C goes to B. So some very simple set of reactions like this with relative rates of, let's say, 1, 2, and 3. And let's say starting quantities of 100, 100, and 100 for A, B, C. And now you can ask the question, what is the probability that A drops below 80? Any point. So start from these and have these reactions firing and ask, what is the probability that in any given trajectory that starts here at this point, 100, 100, 100, at any point, does A ever drop below 80? And that could be relevant. Dropping below 80 could be something, if you're the chemist or the molecular biologist you're interested in. And it's such a simple system, you would think, well, instead of simulating it, I should be able to sit down and just calculate that. Or you can even make it much simpler. You can 10, 10, 10, and 8. And if you think of it, this isn't a probabilistic calculation. If you're asking someone to compute a probability, it has an answer. It has a numerical answer. And so the probability that A dropping less than 8 has a unique definite answer, which you can get at quickly with simulating it. But sitting down and computing the probabilities is surprisingly hard. You start off with the initial set of reactions of what can happen. Either R1 can fire, R2 can fire, or R3 can fire. and then you keep expanding it. And the 3 reactions times 3 reactions times 3 reactions times 3 reactions grows so quickly that it's very difficult to characterize it completely in terms of what is the answer. And this is a theoretical question. Why is a problem that's so easy to state, that doesn't appear to... So the behavior here, if any of you know of chaos theory. So chaos theory is very, very interesting, very complicated math. You can set up a chaotic system where there's a measure of this. Trying to predict what will happen is nearly impossible because the system is incredibly sensitive to the initial conditions. Slightly different initial conditions, you'll get a completely different response. So it means that you can have very simple systems for which it's almost impossible to predict the outcome with any certainty. But these chemical reactions are not chaotic. The math behind it is simple. And the nonlinearities, when they're there, are extremely simple and weak. So for me, this is an interesting question. Why is it so hard? Perhaps we're just not clever about it. Just computing the lattice is, in a sense, like doing the simulation. But there should be, for many such systems, ways that we can just sit down and calculate. What is the answer? Anyways, so I don't know that, how to do that. And you guys will see. It'll be fun to play around with very simple systems like this and try to predict the behavior. But just a few more words on the algorithmic aspect of it. So here, I thought this is where you were going with your question, Don. Suppose that we do this calculation here. So for a given state, we do the calculation. Or for cycle leaping, we figure out that we've been in a cycle and we do the calculation. Well, not only is there a benefit immediately in the simulation for this particular trajectory, because it means that perhaps we can make a step more efficiently. But if you think of it, we're doing these trajectories, we're generating them over and over and over again, 100,000 of them. We're very likely to be in the exact same situation again in some other trajectory. So if we begin caching the information, saying from a given state, here is where we should go, and we have an efficient way of looking up what's in the cache, then the next time we happen to land in that same state, we can again just make use of what we've already computed. And if you think of it, a very interesting hybrid simulation strategy is to just, I don't know how to put this, but imagine that the state space, which is this expanding lattice of probabilities, imagine it's like frosted glass that's frosted. And as you're going through a trajectory, you're wiping off a little bit of the frosted glass, and you see the probabilities. But every time that you've wiped up more of the probabilities, so if you've computed a region of the glass that you've wiped the frost clear of, so then you can immediately make a leap from where you're at to the boundary. And perhaps there, you'll clear more of the glass. Once you've cleared more of the glass, then perhaps you can make a larger leap. And that's a lot of work, but if you're doing the simulation over and over again, then perhaps you're landing in that spot many, many times, and you could immediately make the leaps. So if you're a really clever programmer, it's possible that you can start making larger and larger leaps with each trajectory. Now, it's a hybrid system because in the limit, as I said last time, you could do no random dart throwing. Just compute the probabilities from where you are at the start all the way to the end. But then the problem with that is you're computing perhaps a lot of probabilities for extremely unlikely events that you'll never visit. So the hybrid simulation is you track where you're likely to go, so the regions of higher probability, and you're uncovering those and perhaps making larger and larger leaps. Anyways, so to me this sounds nice and it sounds interesting. If any of you would like to pursue this, I can figure out a way of doing this in the context of the course, kind of as a project, to really sit down and implement this in code and see if it's efficient. I'd be interested in that because I think there's merit to it. But as I keep saying, in this era of modern superparallel computing, it's not clear that any strategy other than the simple naive one is going to win. Okay, yeah, Jacob.
If this whole thing was meant to not waste our random
Yeah.
probabilities, or the random numbers we generate, then couldn't we just use the randomness one bit at a time instead of using the whole thing? So if you go back to the previous thing where it has the interval broken out,
That's a very good suggestion.
you could use the first bit of the random number to just say whether you're at the top half or the bottom half, and then you only have to do that until you have reduced the ambiguity of where you've landed, and so you only use that many bits of it.
Yeah, I like that idea a lot.
It's a pretty similar, reducing randomness to the
Yeah. And basically you're using so you're using the random numbers that you generate, which are generated by an algorithm. You're using them like currency, and you're not spending more than you have to. And from a programming perspective, the random number generator algorithms usually return an integer. So and they have the properties that if you look at the integers bitwise, the bits of the integer are independent. And so then you can use them just bit by bit. And I think that I've heard or read of such techniques that people who really want to exploit pseudo-random number generator, they use the bits like currency more than just using the integers. So that's a very good idea. Okay, let me quickly, unless there are questions, launch into the next topic, which I think is more interesting. Yeah. I shouldn't speak negatively of a topic because that immediately diminishes everybody's interest in this. Okay, so this is going to be now a design problem. It's a design problem that we can tackle given our understanding of how a simple set of chemical reactions behaves probabilistically. The design scenario here is we want to design, and we're not going to focus, of course, on bugs of this kind and any aspects of the bugs. We're just going to focus on the set of chemical reactions, but the set of chemical reactions would be executing inside the computer that is the bug in the scenario. And I set this up, I think, in the second lecture. But the design scenario is that we get to engineer the bacteria once. So we figure out how to modify maybe the gene expression network inside the bacteria to have it execute our code, which is have it implement a set of chemical reactions that we've deliberately chosen. But we get to do that once on paper, like the blueprint. Imagine this is a blueprint for a little mechanical soldier, a little robot, a little nanobot. So you get to do the blueprint once. But every nanobot that you build, then, will be identical to the next nanobot. So you can't have individual nanobots. And in this scenario, which is that the bacteria are designed to kill off cancerous cells, the army of nanobots that you send out, once you launch them, is no longer under your control. You can't directly talk to the nanobots anymore. Well, you can't talk to them individually. So you can't talk to the individual nanobots. And in the case of bacteria, let's say hypothetically, you can't really control the infection. So the infection is just the bacteria, how they naturally, at what sort of infection rate, which is, or concentration of bacteria per volume of tissue, you can't control that. So they're all identical. You can't control, the environment is the same. Each one sees the same environment. You can't control how many there are. Furthermore, each little nanobot or bacteria, I can't decide which one I want here, it can produce the cancer-killing compound, but it does it like a little puff. It just produces a little puff of the compound that will kill the cancerous cells. But the amount of the compound that it produces is fixed. You can't dial it. You can't say, I want it to produce an exact function or a graded function. So given all those constraints, the problem is how you, as the oncologist, how can you control the amount of drug that's delivered? Because you may want to dial that up or down. So let's say this is too high of a dose. You want to dial it up or down. Then what can you do? So someone remind us of what my idea was. So Alex, what was the idea?
You just want to link areas with a certain probability.
With a certain probability. And so I said you can't control anything. You can't control anything individually. So you can't control whether this guy, whether Jason, or whether Alex, so I can't say to Jason, you produce the compound and you don't. But ahead of time, as part of the blueprint, I can say, both of you produce the compound with a probability 0.3. So it's a way, by in advance engineering a probabilistic response, of achieving a coordinated response without any communication, if you think of it. So that's going to be, these are just the constraints. That's the requirement. So if we can engineer this probabilistic response, then we can get what I call as a fractional response. We can get overall in the entire population, if only 3 out of 10 produce the drug, then we get 3/10 the amount that we would get from the total population. And you can see where I'm going with this. It's kind of like the ones and zeros in a bit stream, where the quantity that we compute is the fraction of ones versus zeros. That's what we're going for here. We want to be able to control what goes on by controlling the probability. And that'll be our measure of computation. Yes?
Why not just release 3 instead of 10 bacteria?
Yeah, so that's a good question. But that was part of the set of constraints that I imposed, that you don't get to control the infection. So the infection is you produce some amount of bacteria. Then when they're released, it's the metabolism that decides how many they can do. But of course, this isn't quite realistic. It's not unrealistic in terms of the overall application. It's unrealistic in terms of the constraints that I'm imposing. I'm imposing upon them, yeah. But very good question. Because other people, whenever I pose this, and people who are closer to clinical practice, have all sorts of suggestions. A very interesting suggestion, which I'd actually like to talk about because I haven't done work on it, but other people have, is you can set up, you can engineer bacteria so they talk to each other. How do they talk to each other? Well, they talk to each other by producing certain chemical signaling molecules. And people have created little armies of bacteria that talk to each other and do, like an application of this is called quorum sensing. Quorum sensing is that the bacteria talk to each other and they do something or they don't do something depending upon whether they have neighbors or not. So if you have a bunch of bacteria and you're also in this scenario, imagine that there's the cancerous cell. And a given bacteria, he may not be very confident in his ability to decide, should I attack or not? But if he's surrounded by 100 of his friends, and his friends all say, I think we should attack, then you attack. So this means the quorum sensing is setting up, again, the chemical reactions. That's what we're going to do. We're going to talk about how do we set up the chemical reactions such that the computation happens. And this will be computation with communication. It'll be like a little embedded controller that's connected to other embedded controllers, different sensors. The different sensors decide whether the alarm has been tripped, and if it is, they execute. So lots of interesting applications. But the interesting part and the challenging part for us is not just to postulate how things will work, but to the nitty-gritty, to actually talk about how we could get them to work, and all at the level of chemical reaction. So any ideas? But first, I should say a little bit more. Okay. To set this up. So we want to engineer the bacteria to produce a drug or not produce a drug with a certain probability. But if you think of it, that's not too useful, because this means in advance I'm deciding that I want a 30% response. But it's a 30% response that's static. So again, at blueprint time, I have to say, okay, well, I want a 30% response rate for the drug. Much more useful is if you can dial that probability, or if you can control the probability. So how can we control the probability? I'm not telling you guys that yet, but let's generalize this further. So not only would we want to control 0.3 versus 0.7, we would want that parameter to, let's say, be x. So you can dial x from 0 to 1 for the probability of a given bacteria to behave. But it also doesn't have to be just a yes, no, or 0, 1 type of behavior. You can have more complicated outcomes. You might be, the requirement might be that you want to produce green with probability 0.3, blue with probability 0.2, and C with probability 0.5. And these could be mutually exclusive. So either produce A, or don't produce A and produce B, or either don't produce A and B and produce C. So one of the three can be a probability distribution on different outcomes. So it's getting more and more interesting here. Now we have to set up the chemistry so that something happens or doesn't happen, multiple things happen or don't happen with a probability distribution. But the more interesting part, or you can even have logical combinations, A and B, but we want to be able to control the probability. And this is, I think, absolutely unique in the way that I'm presenting it. Other people don't think this way, is that we can go from quantities to probabilities. So what do I mean by that? So Michelle, what do I mean by going from quantities to probabilities?
Maybe like if there's a lot of X and a little bit of Y.
Yeah, perfect. Then what happens?
Then it changes what your probability is.
Yeah. So the key point is it changes not how much of green we have. So we've got black and white for X and Y. So suppose we've got a lot of black and very little Y. Then perhaps that strongly influences green. But it doesn't influence how much green we have. The amount of green that we have maybe is fixed. It's just a fixed puff. But it influences the probability of getting that puff. So we're going to have the probability of getting a green puff, a blue puff, or a red puff. All mutually exclusive events. We're going to control those probabilities by the quantities. And so this will be the scheme that I'll set up where the input, this is where I already start talking about it, but the input will be X and Y, quantities. And for this particular scheme, it'll be the relative quantity that matters. So X over X plus Y. How much X do we have relative to the total amount of X plus Y? Then the probability of something happening, like producing A, will be a function of X over X plus Y. So the probability of the puff will be controlled. So if you think of it then, the oncologist now who's treating this, he can't talk to the individual nanobot. Can't talk to Jason versus Alex. But he can supply quantities of X and Y. And those quantities of X and Y will be seen globally by everybody. So the entire liver organ gets injected with X and Y. And the relative quantities of X and Y then decide the probabilities of each particular soldier producing a puff of a given kind. So then suddenly we have pretty good control. But I should stop here. Think about it. How would you do this? Just with the set of chemical reactions and with the knowledge that a reaction firing or not happens with a certain probability.
Bacteria. Is it easy to get a certain probability? Is that why that would be like compared to something like having negative feedback?
Yeah.
Is one of those better easier to do than the other?
Not clear. Like, I mean, setting up because you'll see as I present next time, it's kind of like positive and negative feedback that I'm going to set up. But